Hey, welcome back. This lesson, let's take a look at Newton's laws, something you're already familiar with. We'll get to just the fundamentals. I always say that a lot. I say let's get to the fundamentals. But these early videos are really about the fundamentals. And once we have that down, then everything else that we do in science, and especially physics, becomes much easier because everything is really about looking at the situation and trying to figure out what's missing and how to find out what's missing. And so understanding the interactions between forces and motion and things of that nature, let's just jump into this. Let's just take a look. Newton's laws. Hey, welcome back to class. So Newton's laws. There's three of them. You're familiar with that. Let's see how that's going to apply to what we're doing in a larger physics class, and start with the basics, and then we're going to work our way to something more complex with later lessons. Let's just jump in. So we're still on linear motion. So how can we define linear motion? What's the relationship between the variables? So basically, essentially what I'm asking, what we're thinking about is how can we express this mathematically? So it's always about how can we express this mathematically. It's always about that. So let's see, let's go with my favorite. I like blue. All right, so let's zoom in here just a little bit. So if we're talking about linear motion, then we've got motion along the x-plane, right? And so let's just think of, I don't know, a baseball. Baseball's kind of rolling. It's kind of moving in that direction. It's doing its thing, right? It's doing its thing, it's doing its thing, it's doing its thing. This object, we know that it has mass, and we know that that's m, right? And it's accelerating. It's moving in what we would say would be a forward direction. So we're at the point where we always kind of draw our x and our y to define where our positive and our positive both on the x and the y are. We typically define that, and then we know that, of course, going to in this direction here is negative, and down here is also negative, right? So we tend to always draw our coordinate points off to the side. It just is part of the definition of what is given and or what we're assuming. All right, so we've this object, it has mass, and it also is accelerating. And so the acceleration, lowercase a, so nothing new. So the question is what in the world is causing it to accelerate? There has to be something, which means that there is either some sort of push or there's a pull, which you know that's a fancy way of saying a force. And then we denote that with a capital F. Okay, we denote that with a capital F. And then, of course, we look at center mass, right? And so we go from center mass of the object, and then, of course, we're looking at its displacement. So, well, there you go. That's pretty easy. And so then, let's just say we have the same object, but it's dropped, right? And this isn't to scale, this is just a basic concept. Each of those is the same object, I promise, even though they don't look the same. But there is mass here. This object has mass, and there is acceleration. But now that it's vertical displacement, right? And so now that vertical displacement, we know, right, is a change in y. Correct? That vertical displacement, we put a lowercase g to say that it's acceleration due to gravity. All right? And so in this case, it's a pulling force down towards center mass of the planet. So everything on this planet, this Apple Pencil, my cup of coffee, your hair, Everything. This imaginary baseball that's falling in the air, falling down to the air, a paperclip is just sitting on a table. Every single object in the universe has an attraction and a repulsion to all the mass that is around. We're going to find in a later lesson in units that the distance between those masses affects what that overall pulling force is. What we're looking at right now is if we have an object and we release it and it falls, why does it fall? We know it's because of gravity, but it's because of this condition here that we are outlining. And so we have acceleration, we have mass. So we know that acceleration and mass have everything to do with the force. And so one thing we do know is that force times acceleration, or mass times acceleration, will give us force. This is just a fundamental concept. Now, this is not the actual way that the equation is written, but we always think about it. It is a classic way to think force equals mass times acceleration. And we're going to find there's other ways to write force, but it all comes back to one basic concept of mass being accelerated. Some mass is being accelerated in a particular direction, so now it has a change in velocity over some change in time. Okay, so let's move on. Let's look at Newton's first law. All right, Newton's first law. So let's take a tabletop and let's put something on that tabletop. Okay, so we're going to look at the center mass. We always kind of think center mass because it just that is it's not just the edge of it. It's the center mass where all of it is. That has to be overcome. That inertia, and so inertia is basically a resistance to movement. So an object at rest has inertia. So if it's not moving, it is inert. All right. And so in chemistry, like when you're talking about inert gases like nitrogen, we say that it's not very reactive, and so it's referring back to this definition of not moving much, not having much movement, not doing much to it. It takes a lot to get it to move. All right. So even though this thing is on the table and not moving, there is a force pulling this object down, and that is a force due to gravity. But at the same time, the table is pushing back up. And since this object is not moving, the force is equal. So there is a force, an upward force on the table. So this is an upward force. This is our downward force. So we could technically define this as a negative force. It's all right because it's got a direction it's moving downward. Remember, according to our coordinate points that we're defining, x and y, down right here, that will be negative, right? So let's think about it. Forces occur in pairs, and so with everything that we're going to be doing, this is what I'm going to want you to be thinking of, is that if you're talking about a force in this direction, there's another one in an opposite direction, and that's something else we'll look at in more depth as well. If it's going in this direction, there's a force in this direction. There's a force in this direction, there's a force in that direction. There's multiple forces. So since they occur in pairs, what we have to do is we have to look at what's the net result of the force, right? What's the net result of the force? So the net is kind of like what's left over, right? So in this case, the net force would be the force of the table plus the force due to gravity, right? Well, if it's not moving, then mathematically, it doesn't matter what number we pick. So remember, I've talked in previous lessons and in class, just use the number 1. One's an easy number to work with. It just represents 100%. So 100% of the force pushing upward by the table plus 100% of the force being pulled downward by gravity, and since it's downward, that's a negative value. So we can see that we're left with a net of 0, which makes sense. If there's 0 net force, the object is not moving. It's inert. All right? So when we have balanced forces, your acceleration is going to equal 0 meters per second squared. And that kind of makes sense, right? The object is at rest. All right, and so that would mean that its velocity is also 0. meters per second. It stays that way, right? Its velocity stays that way. Newton's law number 2. Unbalanced forces and the acceleration of the object. So if we go back to force equals ma, let's rearrange this equation to actually solve for just the acceleration, right? And so we know that what we would do, right, is you would divide this side by m, so you divide this side by m, correct? Nothing crazy here. So we've got acceleration equals force divided by mass. That's a lowercase m, right? So this is actually Newton's second law, because Newton's second law has everything to do with the acceleration of the object. We have an unbalanced force, right? And so when we have, knowing that we have forces that are in pairs, then we're always taking a look at the net force, essentially the effects of the net force. We're always looking at net force, one way or the other. Sometimes the force in one direction may be 0, and that's fine. But we do include that because it's important as far as the calculations go, because it's not always 0. But if it is zero in any equation that we're defining, we just mark it through. We just put an arrow through it with a 0 to denote it's 0. Let's just get it out of there and let's get this equation down to a smaller version so we can just plug and chug, get an answer, and go home, grab some coffee. So now, looking at this equation here, there are two relationships that exist. So acceleration is actually equal to two things. It is directly related to the force and inversely related to mass. All right? So we see here that when you have a reciprocal, you have an inverse relationship, right? You have an inverse relationship. And right here, this is a direct relationship, right? So this is proportional. It's a direct relationship. Keep that in mind, and that helps when we look at data, and if we try to make predictions about what can happen, we realize if we change if we change the force, we realize what will be the effect. If we change the mass, we realize what the effect will be because of the position of the variables in the equation. All right? Keep that in mind. Rule number 3. The classic equal but opposite. All right? So there's a force that way, and there's a force back that way. And we kind of saw that in the first example. There was that table. The object was not moving, so there was an equal upward force by the table as there was being pulled by gravity. If all of a sudden the object that's on there, bowling ball, whatever it might be, starts to pull downward, then that means the pulling force downward, the negative force value, is actually greater than the upward positive force value, which means the overall net effect would be a negative force. It moves downward. And so if you lift something up, like right now, I want to lift up this cup of coffee. Right now, this cup of coffee, it's sitting here, and gravity is trying to accelerate it downward. However, right now, this table is also pushing back. So I'm going to help this table out. I'm going to help this table get this coffee to my face so I can drink this coffee by accelerating this mass, by adding in some more force, so that the overall net force is more unbalanced in an upward direction. And I got my cup of coffee. Let's move on. Equal and opposite. So here's the classic example. All right, so let's just say we've got, bear with me here, I'm going to try to draw something for you here. All right, so if you haven't figured out what this is yet, this is me trying, oop, that doesn't look like rope. That kind of looks like rope. Let's just say there's a little flag right there in between. All right? So there's a force here and there's a pulling force here. This force is in this direction, and this force is in this direction. Makes sense that we're drawing arrows because since force equals mass times acceleration, and we know acceleration is essentially a change in velocity over a change in time, and velocity is a vector value, which means acceleration is a vector value, which means forces are also vector values. So we draw forces as vectors, all right? And so we basically do vector math here. So if we look at this page here, we would think of this person on the right as having a positive pulling force, and we would think of this person here as having a negative pulling force. And if that flag is directly in the middle, then both forces are equal yet opposite. As soon as there's an unbalanced force and there's more of a pulling or pushing force in one direction, then the net force changes and moves in the direction of that, and so we have an overall net which would be a vector in that direction. Okay. Right now we're just looking at linear relationship where it's either this way or it's this way. All right. So like if something is falling, you know, there is an upward force that would be air resistance, but it's not enough to keep it from falling. Unless you push back just enough, that object's going to fall, right? It's just, you observe it every day, you know this. We're just going to quantify this, and physics loves to make it very difficult and just seriously make it difficult by throwing in a whole lot of letters and variables. So with that said, let's try to take a look at this with a little more detail and quantify it just a little bit, or look at how we would quantify it just a little bit. Let's take a look. All right. Motion of a free-falling object with equal mass of one moving along a horizontal plane. So let's go away. Keep hitting that button. So we've got a horizontal plane. All right. So we've got an object that is moving along this horizontal plane. This object obviously will have a change in displacement. Okay? There will be a change in displacement. And we'll look at this a lot more in class, and definitely look at the lesson where we derive the kinematic equations that we're going to be using throughout this class. And so we're going to use one of those kinematic equations right here. And so we've got delta x, which is the displacement, right? It's delta x. And then we've got a change, we've got the initial velocity times the change in time. All right, and if you think about that, that just comes from taking the velocity equation and you just divide both sides by delta t, and it'll give you this. Plus, we find out that if we add in 1/2 of the acceleration, oh, that doesn't look so good, times time squared. And again, in another video, I explained how we get this equation. Right now, we're just using it. But the time is going to have to be squared if you think about it, because if we look at acceleration right here in this, right? If we look at acceleration right here, inside that is the unit meters per second squared. And so it makes sense that something would have to be true where we have delta t squared so that we can get second squared, and then we can cancel out the second squared on the bottom of the acceleration unit, right? And we'll see that more and more as we practice. But if you just pause and think about it, you realize, well, that makes sense. And then that's eventually, I want to be left with something that is just meters because I'm solving for displacement, right? So this right here, this condition is true if we're solving for the displacement of an object that is moving along a surface. And here is where we will see that acceleration can change. All right, so there can be an initial accelerating force, or there can be an accelerating force afterwards, and then we would apply it into here. So how fast is it initially going, and then we want to know what the acceleration is. All right. So then we have the downward, the opposite of that. So if we drop an object, okay, we drop an object, then let's think about it. Before we drop it, let's just take this whole thing here, right? So now we've got delta y. I don't want to get ahead of myself. Let's just recopy the equation. We got delta y equals the initial velocity times time plus 1/2, oops, I always get ahead of myself with these parentheses, a delta t squared. So now let's think about this. The initial velocity up here, which is say we're gonna say we're dropping this thing from rest. Rest means it is not moving, which means that initially it has a velocity of 0 meters per second. Well, if it has a velocity of 0 meters per second, then the initial velocity here is 0. So we can get rid of it. It is gone. Well, if the initial velocity is 0, then the time there, no matter how much time we're looking at, times 0, it's going to be 0. So now we're reduced down to 1/2 a delta t squared. And if you think about it, the unit for acceleration is meters per second squared. If we have our time squared, then those two units, the second squared units, cancels out, and we're only left with meters, which is what we're solving for anyway, which is displacement, vertical displacement in this case right here, right? So we assume again that there's the air resistance basically is non-existent, and we assume that the friction along the horizontal plane is also basically non-existent. Everything we look at as far as these equations go, it starts with a standard of assuming nothing is opposing the motion, and then just looking at what's the input of force, and then what's the effect of that force on the motion of the object. How do we overcome the inertia? There's a pushing force, for instance. The inertia is overcome. It's greater than the force pushing back on my hand, so to speak. And as that happens, something moves forward. It's accelerating. Time is ticking by, and there's some displacement because the object is first. It's in motion from point 1 to point 2, so to speak. All right. So these two equations, very fundamental as far as just taking a look at motion and Newton's forces and how it affects displacement. All right. So again, I think it's important that you understand how to use these. These are on the equation reference sheet, so just use them, but definitely look at the video so we can have a better understanding of where we get these from, how we derive these things. And then once you do that, you'll have a better understanding of why you use it and when to use it. The how you use it is easy. Once you've got it, you just plug numbers in. Hope this was helpful. Always good seeing you. I will talk to you soon. Take care. Bye. There you have it. Those three laws, and then looking at displacement along a horizontal plane axis or vertical. And again, we always assume that there is no resistance force, whether that's upward air resistance or some sort of resistance force to the motion. So if there's motion this way, there would be frictional force in the opposite direction. Because remember, forces occur in pairs. If it's going up, there's something going down. Something going this way, there's something going that way. Something going this way, something going that way. It just happens. So we'll be looking at that quite a bit. And then later we'll look at the fact that we need to look at forces in that we have force pairs actually in upward, downward, and left and right simultaneously. And we'll be looking at where there's other unbalanced applied forces that are not just left or right and up and down, and then that's when we throw in our angles, and that's when it gets really, really fun. But that'll be for another lesson. It's always good to see you. Stay curious, have fun, work hard on these things. As always, I'm here for you. It's good seeing you. Great talking with you. Bye.